Thanks for joining today's Lunch and Learn. I'm Dr. Joe Schoonover from Fluid Numerics. I am an owner and a research software engineer over here. Today I'm going to be giving you an overview of an introduction to portable GPU programming using AMD's ROCm. What we'll cover today is a model for thinking about GPU hardware and GPU accelerated platforms in general. And then we'll talk specifically about AMD GPU architecture. So this is going to specifically focus on the CDNA1 and CDNA2, in other words, the MI100, MI200 series GPUs. We'll cover an overview of the ROCm software ecosystem so you get a feel about what software is out there in the wild to help you get started with using these GPUs. And then we'll go through some basic examples of how to program applications using HIP and hipfort, depending on if you're in C, C++, or Fortran. And then we'll talk about how to use a directive-based model for programming with OpenMP. Then we'll talk about some strategies to port any codes that you currently have that run on NVIDIA hardware to help you get started with porting those over to AMD GPUs. Let's first talk about GPU accelerated platforms. This is a conceptual diagram of a simple GPU accelerated system. It has one CPU socket and a GPU connected over a PCI bus or PCIe switch. Key features of the system are that the CPU and GPU have their own distinct memory spaces. So you have the CPU RAM on one side and the GPU RAM on the other. And the CPU and GPU are able to exchange information. This could be instructions for things to run or data that you want to work with. That information is exchanged over the PCIe switch. Now the figure on the right is a conceptual diagram of a GPU. At the macro level, you have what's called a command processor. You have, of course, that GPU RAM and a collection of compute units. Inside of each compute unit, you have an additional workload manager. There's typically a higher bandwidth cache. There's also a collection of vector and scalar registers, in addition to an array of compute cores. So when a kernel is scheduled for execution on the GPU, the command processor is responsible for dividing the work to be scheduled onto each compute unit. And then each compute unit, in turn, schedules the work to be executed on the compute cores in batches called wavefronts. These are equivalent to the warps you might have seen on NVIDIA GPUs. And on NVIDIA hardware, you remember that these groups of threads were typically in units of 32 same instruction, multiple thread operations. And then on AMD hardware, this is going to be your 64. Now, just to help you, if you've already been programming on NVIDIA hardware, you may be familiar with some terminology already to describe the GPU hardware, just to help you kind of translate between the two of them. What NVIDIA called a workload distributor, AMD refers to as a command processor. What's called a streaming multiprocessor. This is similar to the compute unit, and then again, the warp is similar to a wavefront. So the way we usually think about performance, it's going to be one of two metrics. It's bandwidth, which is the amount of data that you can move or process per unit time. This is typically measured in gigabytes per second. Or we think about performance in terms of flops, so the number of floating point operations you can do per second. So typically what you'll see on modern systems these days, the bandwidth that connects the CPU RAM to CPU, you'll be on the order of about 100 gigabytes per second. On the GPU side, between GPU RAM and GPU is about 1,000 gigs per second. And the PCI bus is fairly slow, but things are getting better in this realm with PCIe 4 becoming more prevalent. We're seeing things more like 64 gigs per second bidirectional. But in general, when you're on these GPU systems, this connection between CPU and GPU is usually the slowest or the least performant component of the system. But if we compare, if you get your data over onto the GPU, you have the potential to do about a factor of 10 better than what you can get on the CPU side if you're in a bandwidth limited regime. Now in terms of the compute performance, the CPU performance, you can expect to get about a teraflop of performance, and on the GPU side, about 10 teraflops is what you can expect. Now, of course, with some of the new AMD GPUs that we have, there are ways to get much, much higher than this 10 teraflops if you can sacrifice a little bit of precision, or if you can exploit matrix style operations. So we'll talk about that next. Back in about 2012, AMD introduced what's called the Graphics Core Next GPUs, and multiple GCN generations have been released since 2012, with the most recent being the GFX 9. So if you've been on the Vega systems, like the MI25 Frontier Edition GPUs, I think those were back in 2017. They use what was called the Vega instruction set architecture. Now, AMD GPUs from this period were then divided into two categories. We have what's called RDNA and CDNA. The RDNA GPUs are designed and optimized particularly for gaming purposes to maximize frames per second, and AMD CDNA GPUs are optimized specifically for computing purposes. So they have things like 64-bit arithmetic, and they're designed in such a way to meet the requirements of the applications they expect to run on them, which is really general purpose scientific applications. What we're going to be talking about today is the CDNA line of GPUs. Now keep in mind that there is a set of RDNA GPUs that are supported in the ROCm ecosystem. So here we're looking at a conceptual diagram of the GCN hardware layouts. Consistent with our previously discussed model of a GPU, the AMD GCN GPUs have a command processor shown here at the top. It has HBM or GDDR memory, so that global RAM is going to be either the HBM or HBM2 or GDDR memory. And then we have a L2 cache that is shared across all the compute units. Then the compute units on the AMD GPUs are divided into these blocks that are called shader engines. So a shader engine shares a workload manager, and then there's compute units underneath this. And each of those compute units have a wavefront schedule. So you have command processor sends work to workload managers for the shader engines. The workload manager and the shader engine will pass off work to each compute unit, and each compute unit will independently work on scheduling work in series of wavefronts on each compute unit. So now we'll take a look at a specific block diagram for the CDNA1, which is the MI100 series GPUs. So here what we're looking at is a block diagram of AMD's MI100 GPU. The MI100 GPU is connected to the host through a PCIe 4 interface, which provides the 32 gigabyte per second one-way bandwidth. The GPU is comprised of 8 shader engines, and each shader engine has 15 compute units, giving 120 compute units in total. The global memory size is 32 gigabytes with a peak memory bandwidth of about 1.2 terabytes per second. The L2 cache is 8 megabytes in size. It's shared across the entire chip. The way it's sort of parsed out is the 8 megabytes is divided into 32 slices. So this is 256 kilobytes per slice. And each slice on that cache can sustain 64 bytes per cycle. So if you put all this together, multiply by the memory clock frequency on the system, you get about 3 terabytes per second out of that L2 cache. So each compute unit on the MI100 GPUs has 4 vector execution units, and they also are equipped with what are called matrix engines. And the matrix engines implement an instruction called a matrix fused multiply add. In addition to those vector execution units, there's 4 vector register files, as well as 64 kilobytes of high bandwidth local memory. With these specifications, the theoretical performance for double precision arithmetic on the MI100 GPUs is 11.5 teraflops. The matrix engines support in the MI100s FP32, FP16, and bfloat16. So if you're at FP32, you can get about 45, 46 teraflops. bfloat16, you can expect 92 teraflops. And if you do that, straight FP16 operation, you can get to a whopping 184.6 teraflops in one GPU. Now, if you want to leverage the matrix engines in your code, there's a handful of ways you can do that. ROCblos, using the ROCblos library, is certainly the easiest way to go about it. And there are also compiler level intrinsics you can insert in your code if you're building using the hipclang compiler. So if you're doing hip code, you can insert the intrinsics to do these matrix operations. So now I want to talk about the newer CDNA2 GPUs. So this is the MI200 series GPUs. So this is a block diagram of the CDNA2, what's called a multi-chip module. So it consists of two graphics core dies. So on one side here, in this teal box is one graphics core die, and on the right we have another graphics core die. Now the graphics core die you can think of as being its own GPU, and certainly when you plug one of these multi-chip modules into your server, what it appears to your operating system as is two distinct GPUs. Relative to the CDNA1, the MI100 architecture, there's a number of improvements. So the matrix engines on CDNA2 now support the FP64 matrix fuse multiply add operations. And the peak performance on the MI250X, which are the liquid cooled modules that have the two GCDs on them, the peak FP64 MFMA is about 95 teraflops. If you're doing vector FMAs, you're at about 47, 48 teraflops on the, again, this is on the 250X. You also have what are called packed FP32 instructions. So if you're doing things with single precision floating point operations, you can actually stack two of the FMAs for FP32s to be run on the same clock cycle. So when you're programming in HIP, there is a function you can call to do the packed FMA. That is certainly an easy way to take advantage of that. There's also increased global memory capacity. So for each graphics core die, so again, for each half of this multi-chip module, there's now 64 gigs of HBM2 memory relative to the 32 gigs that we had on the MI100. So if you're working on the 250, the MI250 or MI250X, you have 128 gigs of memory available on board that GPU. In the MI200 series of GPUs, you have the MI210, the 250, and the 250X. The MI210 is just going to have one of the GCDs active on the GPU. It really is just one GCD. If you're on the 250s, you get two GCDs, but only 108 of the 112 compute units per GCD are active. And if you're on the liquid-cooled version of the MI250X, 110 of those compute units are active out of the CUs, out of the box. So now that we've discussed the hardware, let's move on to the ROCm software ecosystem. ROCm is an open source software platform developed by AMD for GPU accelerated computing. It consists of frameworks, libraries, programming models, compilers, the ROCm runtime library, as well as programmer and system utilities. The frameworks that are currently supported, so these are high-level programming languages and libraries. We have TensorFlow, PyTorch, CAF, CAF2, Cocos, and Raja. The ROCm accelerated libraries provide options to transition from CUDA accelerated libraries. They include things like ROCblos, ROCFFT, ROCsparse, ROCthrust, and ROCrand. There are a few programming models in ROCm that are supported, including HIP, OpenMP, and OpenCL. HIP and OpenCL provide a kernel-based approach towards portable GPU acceleration, while OpenMP provides the directive-based approach. As I mentioned before, all the ROCm code is open source. You can find any of that code online on GitHub. And AMD has sort of divided all that source code into a few different organizations on GitHub. So you have Radeon Open Compute, which contains repositories for the ROCm core technology as well as documentation. There's the ROCm developer tools and programming language. So it's going to have things like HIP, ROCprof, the ROCgdb, the debugger, tools like that. And then there's also the ROCm software platform repository. This contains a lot of the accelerated libraries and additional things like hipfort. You can find documentation online at docs.amd.com. There's also the AMD Developer Zone, which has lots of videos and tutorials and things you can dive into independently, so you can get spun up on a lot of the software that's available. And a new thing that's come up recently that I've quite enjoyed a bit is the AMD Lab Notes. There's been a lot of blog posts that have real-world examples of programming, scientific applications, and optimizing performance for AMD GPUs. So now we're going to shift gears and we're going to talk a little bit about coding. And we'll start off by discussing how you can get started with programming GPUs using HIP. So HIP stands for the Heterogeneous Compute Interface for Portability. It is an open source C++ API and kernel language for programming both NVIDIA and AMD GPUs. With HIP, you write portable source code that is passed through the HIPCC compiler wrapper, which determines at compile time whether it should use NVCC for NVIDIA GPUs or the HIP Clang compiler for the AMD GPUs. When you're writing code for a GPU, remember that the host and device memory are distinct memory spaces. To allocate memory on the GPU, we have the hip malloc routine. As input, hip malloc expects a pointer and the number of bytes to allocate in that specific order. And to copy data between the host and device, HIP provides hipmemcopy. The hipmemcopy API expects 2 pointers as an argument, the destination pointer as well as the source pointer, the amount of data that you want to copy, and then an enumerator that indicates the direction the copy is going. When you reach to the end of your code or you no longer need access to a GPU pointer, you can free that pointer simply by calling hip free. So let's take a look at a very simple example how this might work. So if you haven't programmed GPUs before, this may feel a little bit weird, but you have to keep in mind that for every host side pointer that you have, you'll usually end up with a GPU counterpart in your code. So in some sense, it starts to duplicate the amount of code that you have, or it doubles the amount of code that you have. So here what we have, of course, at the top, we're going to include the HIP runtime. We've declared a float for a device array. Now, what you name the array, of course, is up to you. Some people use a convention of underscore dev or underscore GPU for device or GPU. And then the host side pointers are, again, whatever you want to name them. So here, F is malloced on the CPU. It's it's an array of size n. It stores floats. If we wanted to allocate a device copy of this, we would call hipmalloc. We'll pass fdev, which is our device pointer, and then again that same size. Suppose you've done some initialization inside of here. You've set some values for f by, I don't know, reading from file or something else, and now you want to copy that data stored in f to fdev. So again, we'll call hipmemcopy. The first argument is the destination pointer. Second argument is the source pointer. Third is the amount of data, so this would be the size of the array or the size of the subset of the array if you wanted to only pass a portion of it. And then we have an enumerator here that indicates direction. So the enumerator that we would use in this case, because we're copying from host to device, would be hipmemcopy host to device. Now suppose you've done some operations on the GPU and now fdev has been updated, and you want to get that data back to the CPU for maybe another kernel to run on the CPU, or you want to write to file. You would call hipmemcopy again. In this case, since we want to go from device to host, we would put the destination pointer as the CPU pointer, the source as the device pointer. We still have the same size, same amount of data that we want to copy back. And in this case, we use the enumerator hipmemcopy device to host. And then, of course, at the end of the code, keep memory tidy. We'll free the f pointer as well as the fdev, so the device pointer. Now we're going to talk about how to write and launch kernels. Remember, GPUs are capable of executing thousands of threads simultaneously. And the way we talk about this on GPUs is the entire collection of threads that get executed or that are used for execution of a kernel is called a grid. And that grid is divided into blocks. And so we have these light gray grouping of threads and this dark gray grouping of threads. This would be each of these sort of groupings would be called a block. And then within each block, there's individual threads. And the way you access an ID or an identifier for that thread is by its block ID, so which group it belongs to, or sorry, which block it belongs to in the grid, and then you have its local thread ID within that block. So if I were in this block here, so let's say this first light gray section is block 0, this is block 1, okay, and then this is block 2, etc. Inside of, let's say, block 1, I have thread ID 0, 1, 2, and 3. So to get that local thread ID within the blocks, you can use the thread IDX intrinsic. Now to get the block ID out of this, you can do the block IDX. And if you're trying to, which happens a lot in these applications, is you try to calculate a global thread ID using the local thread ID and the block ID, we can use the block dim intrinsic as well. So again, that block IDX gets you which block you're in. Thread IDX gets you which local thread ID you are within that block. And then block dim tells you the size of each of those blocks, so how many threads there are per block. You can also get the grid size using the grid dim. So this reports the total number of threads in the grid. Now, to launch your kernel from your C++ code, you'll specify the kernel name. You'll specify using what's called a dim3 type to set the number of blocks and then the number of threads per block. And then you'll pass the arguments that you have. If you also wanted to, there is a HIP API intrinsic for this. It's called the HIP launch kernel GGL. It does the same thing. But you'll pass the kernel name, number of blocks, threads per blocks, and then the arguments one after another. If you're more familiar with that CUDA syntax, this is certainly fine. So there's two ways to launch those kernels. Okay, so we're going to take a look at an example of a very simple application on the CPU side and how we might put this on the GPU. So here we have arrays A, B, and C. They're going to be of size 1,000 here. We'll malloc them on the CPU side. They're floats. And suppose we've initialized them somewhere up here, and then we get down to our main compute section, which does a for loop to add the elements of A to the elements of B and store them in C. What we want to do on the GPU is expose the parallelism that is inherent in this for loop. So when we write the kernel, the first thing is when you declare a kernel that's run on the GPU, you need to use either the global or device specifier. Typically, you're gonna use the global type specifier. What this means is that this is a kernel that is run on the GPU, but it can be called from either the CPU or the GPU. It's a void. Every GPU kernel is going to be a void type. You'll give it a name. Here we'll call it vec_add. And then we've got our input arguments are A, B, and C. And of course these are expected to be pointers that are on the GPU. And I'm going to pass the size of the array by reference, just because we're going to need that for our for loop. So if you think that, so we have an array of size 1,000. Let's suppose that we were to, for example, use 100 threads to run this. Well, I guess one way we could do this is have thread 0 add A0 and B0, store that in C0, and thread 1 would do A1, B1 stored in C1, and so on until I get to thread ID 99. And then I would just kind of go back through the loop here because I still have more data to add up. We'll assign more work back to thread 0. So then we'll start over. We say thread 0 does A100 plus B100, store that in C100. Thread 1 does 101. A101, B101, store that in C101, etc. So what we want to do is, if I know my thread ID, my global thread ID in the kernel launch, so here I have 100 possible threads in this example. I want that thread, so let's think about thread 0. Thread 0 is going to do index 0, it's going to do index 100, 200, 300, 400, etc. So what it's actually doing is thread 0 is going to do its own, it's going to access A at thread ID, B at thread ID, add those together, store at C thread ID. Then it's going to stride by the total number of threads we have, in this case 100, and do the same thing. So what we'll do is, instead of doing I++, which does a sequential iteration here, we'll do I starts at my thread ID rather than 0, goes all the way up to n, non-inclusive, and we're going to stride by some stride value. Well, the stride value we want to use here is the total number of threads, so the grid dim.x, and then we calculate my thread ID by doing thread ID x.x, so my local thread ID. And then we add to that block ID x.x multiplied by the number of threads per block. So this gets me the global thread ID. I have my stride, and so now I break this loop up. So what happens here now when I launch this kernel is that, again, all the threads are going to do this instruction in parallel. And then each thread is only going to do a subset of the original amount of work. So that should expose a good deal of parallelism that we can control by changing the grid and block size. Now, when we go to launch this kernel, of course, in our main code, we'll include that hip runtime header. We'll declare device copies for A, B, and C. We'll allocate the device array for A, B, and C. So again, we'll call that hip malloc. We'll do our hip mem copies somewhere in here to get the data we need for A and B onto the GPU. And then we can launch that kernel. So to declare the number of threads per block and the number of blocks, we'll use the dim3 type, which comes from the hip runtime header. Here we'll say 256 threads in the X direction, 1 in the Y, 1 in the Z. And then the number of blocks, we'll just go ahead and safely do n over 256 plus 1, just to make sure we're capturing the entire array. Then you can launch using that chevron syntax. So here we have vec add and block and thread, and then we pass adev, bdev, cdev, and then the size of that array. So this will effectively execute the same thing we have on the CPU side, and of course, after running this vec add kernel, we would copy the values stored in cdev back to C using hipmem copy. So some rules you need to keep in mind when you're writing these kernels. The number of threads per block is limited. On most GPUs, this is 1,024 threads per block. Each block is executed independently. So order of execution is not guaranteed. So keep those things in mind. Now that we kind of know how to manage memory, we know how to write kernels, we know how to launch kernels, we now need to talk a little bit about how to build your code using hipcc. Now there are two environment variables you can use to control the target platform that you want to build for. Of course, if you're on a system that has a GPU on it, hipcc will automatically detect that for you and define the appropriate parameters during the build. If you're on your own system where you don't have a GPU, or if you're building your code using some continuous integration infrastructure, you can control the target platforms that you build for. The first, you will use an environment variable called hip platform. You can set this to either AMD or NVIDIA. And then you have the GPU target environment variable, and this is where you're going to specify the architecture code. So to compile your code, you would just use hipcc as you normally would any other compiler. Just for reference, some of those architecture codes you may encounter in the wild. For the AMD Instinct GPUs, the MI25s you'll see is GFX 900, MI50s is GFX 906, MI100 GFX 908, and if you're on the MI200 series GPUs, it'll be GFX 90A. So if you're working with Fortran applications and you've done things with CUDA Fortran, or if you've done sort of the CUDA C plus Fortran hybrid, the mixed language programming stuff, there is support for that within ROCm using a tool called hipfort. Now, if you've done CUDA C plus Fortran, this will be a pretty straight conversion for you. If you're done CUDA Fortran with the PGI compilers, there's still some effort out there to figure out what to do to get that kind of syntax into Fortran, but it's currently not supported underneath ROCm. Hipfort, it's a Fortran interface for HIP, as well as the ROCm accelerated libraries. Much like HIP, we have the same API, or we have a similar API for allocating memory and copying memory. We still have hipmalloc, which takes in a pointer and then the amount of memory that you want to malloc. Now the pointer here could either be a Fortran pointer or it can be a type C pointer from the ISOC binding library. Additionally, you don't have to specify the size explicitly. There are optional parameters where you can pass in the host side Fortran pointer as the argument through what's called the source or the mold, and that will calculate the size underneath the hood for you. Now in Fortran, the output of these calls, you get an integer error code, which you can send off to some helper routines that either you write or that are provided by the hipfort library to check those errors for you. We still have hipmemcopy, which follows the same syntax or the same order of arguments as the C++ counterpart. So we have the destination pointer, the source pointer, the size, and then again an enumerator to indicate that direction. Now the destination and source pointers, those can be Fortran pointers or type C pointers as well. And again, the output here is an error code. To deallocate memory on the GPU, you can also, again, you're using that hip-free call. And again, you're passing either a Fortran pointer or C pointer that points to that memory on the GPU. And again, we get that error code as output. Now, when you're launching kernels from Fortran, there are three ingredients, and one of them we've already covered. So we have the hip kernel, which is written in that C, C++ syntax. And then what you want to do is then write a launch wrapper. So this is a C or C++ code that actually launches the kernel using the chevron syntax or the hip launch kernel GGL API. And then we expose that wrapper to Fortran using a subroutine interface with ISOC binding. So we're going to do the same example as we did before, but now just written in Fortran. So here we have real allocatables, A, B, and C. So we're going to allocate them of size n. Here's 1,000. We're going to have a do loop from 1 to n, and then we'll add A to B and store it in C. So on the GPU side, we have, again, that vec add routine that we wrote before that runs on the GPU. And now what we're also going to add now is this vec add wrapper. So this wrapper routine, its sole purpose is to launch that kernel in this case. So here we're using that chevron syntax, the grid and block size, as well as the A, B, and C arguments and n. A key thing that makes this work is wrapping the wrapper in a region that we declare as external C or extern C. Okay, so now we're going to talk about what you need to do to expose that kernel to Fortran code so that you can call it as if it were a Fortran subroutine. So at the top of the program, we're going to use the hipfort check and ISOC binding modules. And then we have this interface definition. Now the interface is what's going to turn that vec add wrapper method into a Fortran subroutine for us. So we'll declare the interface as a subroutine. Here I'm calling it the same thing as I call the C++ wrapper. You can call it whatever you want, but it's good practice to keep it named the same so that it limits confusion when other people look at your code. Now the order of the arguments for this wrapper should match the order of the arguments for the C++ counterpart. So here we've got grid, block, A, B, C, and N. And then we're going to bind that subroutine to a C object called vec_add_wrapper. Now when you're defining this interface, you do need to declare modules again. So we have ISOC binding we're going to use so that we can use the C pointer and C int types. And then we're going to also use hipfort types so that we can define the grid and block size. Now it doesn't matter if you're using Fortran pointers or C pointers in your code for the GPU memory. Ultimately, when you get to launching a kernel, you do need to convert those Fortran pointers to C pointers. So keep that in mind. So here we have A, B, and C are type C pointer. The integers, it's good practice for portability reasons to declare their kind as a C int. And we're going to pass that guy by value. So this, in addition to the wrapper we wrote previously and the kernel before, is now what we need to essentially call vec_add_wrapper from the Fortran side as if it were a subroutine. Now, if you're using allocatables on your CPU side code, you will want to convert them to pointers. This is necessary for the hipmemcopy API. If you don't have them declared as pointers, you won't be able to do hipmemcopy. So we'll declare A, B, and C as pointers now rather than allocatables. And then we have the pointers for device versions of those arrays. We have A, B, and C, or DA, DB, DC. And we'll initialize them to null pointers. A, B, and C are allocated here. And then we have the device arrays are allocated down below. And here is what I'm showing you an example of how to use those optional arguments I mentioned before. So we're wrapping, so hipcheck is a subroutine call from the hipfort check module to check the error codes that come out of the hip API. So you have call hipcheck, we got hipmalloc, device array A, and we're going to use A, the host side array for A, as the mold. And what that means is that underneath the hood, hipmalloc is going to use the type of A as well as the size of A to determine how much space needs to be allocated. Okay, now we're going to do data transfer from host to device, assuming that we've done some initialization for A and B. So again, hipmemcopy destination source, the size of the array. Here you just, in Fortran, you're just going to use the length of the array. You don't need to include the type because we can figure that out at runtime. Then we have the enumerator hipmemcopy host to device. Do the same thing for B. And now when we want to launch our kernel, we can call vec_add_wrapper. This was that interface we defined previously, passing the grid, block. And then to convert those Fortran pointers to C pointers, we can use the cloc intrinsic from ISOC binding. So you got cloc DA, DB, and DC. To build hipfort code, you can use the hipfc compiler. Now hipfc can be used to build both your Fortran code and your C++ and hip code. So hipfc, like hipcc, is a Perl script wrapper. It's going to determine based on the file extension whether to use your preferred Fortran compiler or to use hipcc. And then hipcc is going to make its decisions whether to use nvcc or the hip client compiler. So you still have the options to set the hip platform as well as the GPU target using environment variables. You now also have the ability to set the preferred Fortran compiler that you want to use by using the hipfort compiler environment variable. So this could be gfortran, it could be AMD flying, it could be ifort, it could be whatever you prefer to use for building your host side code. So let's talk a little bit about porting from NVIDIA GPUs to AMD GPUs. This is a strategy that we try to follow using some of the tools that are available out there in the ROCm ecosystem. So if you're starting with CUDA C code plus Fortran, or CUDA Fortran with that's built with the PGI compilers, there's different paths you can take. Now, generally on the right-hand side, we all follow the same exact steps. If you're at CUDA C and CUDA C plus Fortran, you can use scripts, the hipify scripts or hipify Perl scripts to convert your CUDA code to hip code. And then you have some adjustments to make to your make system to get things working properly. With CUDA Fortran, there's another tool called GPU Fort. It takes a little bit more hand editing with this route because this tool is still actively under development, but it gives you one route towards doing that. No matter what you do, if you're currently running on NVIDIA hardware, it's important before you go into this porting process that over here, before you run through the hipification or GPU Fort process, that you have a way to build your code and test your code on NVIDIA hardware before you even get started. Once you do that and you run through the hipification process, you should be able to get the exact same answer with the exact same performance on that same NVIDIA hardware. So coming into this with a good benchmark in mind that exercises every bit of your code that you need to is important. Once you can verify that you can do that, then we recommend changing those environment variables and building for AMD hardware and getting on some AMD hardware and testing out what's going on there. Now keep in mind that if you've written code that runs well on NVIDIA hardware, it's possible that you're not going to get perfect performance or the best possible performance on the AMD hardware. These are different animals, and you do have to spend some time profiling and performance tuning in a lot of cases to get the performance where you want it to be. So now we'll talk about GPU acceleration using a directive-based approach with OpenMP. In this section, you're going to learn about the OpenMP 4.5 standard as well as what you can expect in terms of compiler support. Then we'll talk about OpenMP target regions and how to accelerate do loops. And then we'll discuss how you can build your OpenMP accelerated applications. As of OpenMP 4.5, there's now support for what's called a target region, which is meant to indicate a region of code that you want to accelerate and offload to GPUs. Now, your job when you're working with OpenMP is to insert directives to the compiler that are usually in special comments in your code to hint at acceleration strategies. Now, the nice thing about directive-based approaches like OpenMP or OpenACC is that is a lot less changes to your code that need to be made. And since the changes are sort of hidden inside of comments, you can easily not have these impact your CPU side code. There is support for both Fortran as well as C and C++, and you can build your code for multi-core CPU as well as multiple GPU platforms, all with the same set of directives. Now with OpenMP 5, there's more features that are coming our way, including support for what are called deep copies. This is specifically helpful for Fortran applications that use derived types. And then there's also APIs for accessing some of the pointers that OpenMP creates for you for the device memory. So if you have code that in some sections uses OpenMP for its acceleration, and you have code that's using ROCm accelerated libraries, you can mix those codes or those sections of your code using the OpenMP 5 memory management, which is quite nice. So with OpenMP, you can use the OpenMP target directive to mark regions of code that you want the compiler to offload to the GPU. When you use an OpenMP target region, the map directive is used to indicate variables that you want to copy to the GPU and from the GPU. So I've shown on top here an example for Fortran as well as for C++ first. We're inserting our pragmas or our directives inside of comments, and the comment is always started with this pragma. So in Fortran, it's $OMP. In C++, it's pragma OMP. And then you have the directive or the compound directive that provides the hints to the compiler about what to do. Again, that target directive is going to create a target task, which is going to be executed on the GPU, and the map clause is going to indicate the data that we need to copy back and forth. Here we have the target map directive here indicating that A and X are going to the GPU. You could see why we would only want to copy to the GPU because A and X are used on the right-hand side of an equal sign. meaning that we're only reading these guys to do operations to update AX. Now AX is used on the right-hand side and on the left-hand side, so we're reading and writing. So we want to map both to and from the GPU. On the outset, if you just have a target region, the target region is going to run with a single thread. And if we're running with a single thread, remember that the GPU clock frequency is lower than the CPU clock frequency. So running with a single thread on a GPU is going to get you far worse performance. So you do need to add some additional directives to expose some parallelism in your application. Now in this particular example, we have this I and J loop that can be done independently. And then we have a reduction done inside of here. The main directives you'll find yourself using when you're parallelizing these do loops is the teams directive. The teams directive is going to create what's called a league of teams, and each team is going to have a single thread per team by default. The distribute construct is used to specify that the do or for loop iterations are going to be distributed amongst the teams. In this particular case, if we just do teams distribute for, so this outermost loop, the J loop, is going to be broken up into equal parts and distributed across those teams to be executed in parallel. Now the parallel construct is going to populate the teams with multiple threads. So this is sort of that same echoing of that two layers of parallelism that we've seen before with GPUs, where we have this sort of macro level of parallelism here indicated by the teams, and then the micro level, which is the threads within the teams underneath that. Now, if you want to expose parallelism in tightly nested loops like we have here, an I and J, you can use the collapse intrinsic, which if you've done OpenACC, this looks very familiar. What it's essentially going to do is flatten these two outer loops as if they were one big do loop and distribute that work across those teams. Remember that OpenMP is a standard, and it is implemented to varying degrees in different compilers. We highly recommend that you use AMD Clang and AMD Flang, which comes with a ROCm installation, or if you're on an HPE Cray system, that you use the Cray compilers. Now, if you want to use the GNU compilers, you will need to build the GNU compilers from source and enable that OpenMP offloading when you build those compilers. There's a few flags that you need to send to the compilers to enable GPU offloading. The first is -f OpenMP. This enables interpretation of the OpenMP directives in your code. You'll also need to set the GPU target, and this is set in two flags. So you have f-OpenMP targets and x-OpenMP target. This is where it's going to be the specification for the AMD GPU or NVIDIA GPU, and then you have the target architecture. Now, the one thing we know when we're building these codes is that in one column we have the target for the AMD GPUs. What you're going to use for that target is AMD GCN, AMD HSA, or if you're building for the NVIDIA GPUs, you're going to use NVPTX64-NVIDIA-CUDA. And you'll notice that the NVIDIA GPUs all have this SM_ prefix on them, and for the most part, these AMD GPUs have the GFX prefix. Now, there are some GPUs that are supported in AMD's lineup that aren't prefixed with GFX, but this for NVIDIA is pretty consistent. So what you can really do in your make systems is you can have a variable for someone to specify the target architecture, and if it starts with SM_, you can set the f-OpenMP targets to this value for the NVIDIA GPUs. Otherwise, you'll use the AMD GCN, AMD HSA. So if you go through some of the examples in the code labs, I'll provide links to at the end here. You'll see some examples about how to do that. So to piece this all together, what your compilation would look like, either using AMD Clang or AMD Flang, you'll have f-OpenMP minus f-OpenMP targets equals the target, which again is going to be one of these in the top row. And then you'll have the target architecture, which again is any of these architectures for the AMD GPUs or the NVIDIA GPUs there. You can pass any of your other compiler options and then the path to your source code that you want to compile. So here's those links to the code labs we have available. So if you just go to fluidnumerics.github.io/scientificcomputingedu, in the navigation, there's a tab for code labs. You'll find 4 of those that are available, and you can choose them based off the language you want to work with, as well as the API you want to use for GPU acceleration. These are very basic code labs that walk you through a stencil code that does a 2D smoothing operation, but just should give you a feel for programming with OpenMP or HIP to run on GPUs. Now, if you're interested in additional support and you want to learn more about fluid numerics, we do things called mentored sprints. We can help you take a look at your code, identify some of the compute resources you want to run on, and help you come up with a plan to get ported over to those AMD GPUs in a matter of 5 weeks. We've been doing these over the last couple of years with customers and have had a lot of fun doing them, and have seen some folks get migrated fairly quickly, as well as get some performance code on the other side. If you're interested in that, definitely reach out to us at support@fluidnumerics.com. Of course, you can check us out on our website at any point at www.fluidnumerics.com. So with this, let's go ahead and open up the Q&A.